Unit 4 is all about introductions to reactions. First off is physical versus chemical changes. Go ahead and pause and read through those. So in a chemical change, new substances are formed. While in physical changes, we're going to have the same substance, but it may look a little bit different. Remember that all phase changes are physical changes because only intermolecular forces are being broken, so the substance remains the same. Ambiguous changes would be dissolving of ionic compounds. Because like we saw on the previous slide, ionic bonds are broken along with the formation of ion-dipole interactions, so we have processes that have physical and chemical pieces in that, making it ambiguous. But most changes can be classified as physical or chemical. So here are all of your phase changes. Make sure you know all those words are physical changes. Looking at these particulate diagrams, figure out if a physical change or chemical change occurred. Restart when you have your answers for those three. So for the first one, it should be physical because the particles just spread out. So here they were kind of bunched together, and now the red ones are all spread out. So the second one should have been chemical. We broke these bonds here, and then we formed new bonds between the red and the green ones. And then the last one also should have been chemical because the bonds were broken. Here they're diatomic, and then over here they're monatomic, so the bond was broken. Go ahead and pause the video and figure out this one. Restart when you're done. So we're dissolving an ionic compound. And dissolving an ionic compound is going to have both chemical and physical because, again, we're breaking ionic bonds and we have interactions between the ions and water molecules, which are ion dipoles. Go ahead and pause and read through here, paying close attention to the underlined sections. Go ahead and pause the video and write the molecular equation for each of these, including your state symbols. Restart when you're done. So for the first one, we have a solution of sodium hydroxide and it has group 1A. Group 1A is going to be aqueous. Acetic acid is a solution, so that's going to be aqueous. We have a double replacement reaction. So the H went with OH to make H2O, which is a liquid. And then sodium went with acetate to make sodium acetate. Again, all group 1As are going to be aqueous. So for this next one, we have fluorine, but fluorine's diatomic, so it's F2 and it's a gas. We have a solution of potassium chloride, but again, it's group 1A, so it would have been soluble. Single replacement, fluorine kicks out chlorine to produce chlorine gas, because chlorine can't be by itself, and potassium goes with fluorine. Again, potassium's group 1A, so they go together 1 to 1. More than likely, on the AP test, you'd be given the entire reaction and just asked to balance it or to write the net ionic equation from that. So given these equations, let's go ahead and do the net ionic since that's more likely how you would see it. Remember, for a net ionic, you're going to break apart all strong acids, strong bases, and soluble salts. Restart when you have your answer. So here I have the complete ionic. And the complete ionic breaks apart my NaOH because that's a strong base. It kept together acetic acid since that's a weak acid. Water stayed together since it's a liquid. And sodium acetate broke apart since that's a soluble salt. Again, this would be the complete ionic. To get my net, I cross out all spectator ions. And then I bring down what's left. Make sure that your equation is balanced. If it's not balanced, then you will not get the point, and make sure that you have charges on things that should have charges. In this case, it is balanced, so this is my final answer. So again, this is my complete ionic. My spectator is potassium. And so you should have had a 2 in front of chlorine ion and a 2 in front of fluorine ion. Remember, make sure that you have your charges. I don't need the state symbols for either of them. You can definitely include the state symbols, but you are not taken off for not including the state symbols. Where you do lose the point is not having it balanced, not having the correct charges, or not bringing down subscripts like you should have. So go ahead and pause the video and figure out which of these best represents the reaction given here. So the first step I would do is write my equation. And so hydrogen gas and iodine gas are both diatomic. So that eliminates D and C because we have single and single. So it's either A or B. A has 3 big circles, while the products have 6. So A does not follow the law of conservation of mass, so the answer must be B. You'll also need to be able to do stoichiometry. Besides just regular stoich, you need to be able to use the ideal gas law, which we've seen previously is Pivnert, to solve for moles and then do stoich with that. Or maybe you need to use molarity, which we've also seen previously, moles per liter. These were your steps for stoich. Remember, when you don't have a calculator, set it all up and reduce. So pause the video and try this one. Try solving it without a calculator since it is multiple choice. So again, set up your reaction or set up your dimensional analysis and start reducing things. If you get stuck or once you're done, restart the video. So for this one, we have 2 given amounts, and so this is a limiting reactant problem. So I'm going to start with my 98 grams of zinc. I need to convert grams of zinc to moles of zinc. Because it is multiple choice, I can round that to the nearest whole number. If it was free response, I would definitely be using all of my decimals from the periodic table. I need my mole to mole ratio. So step 1 is convert to moles. Step 2, moles to whatever I'm looking for. I'm trying to find hydrogen. I get the numbers for my mole to mole ratio from the balanced equation. And then 1 mole of hydrogen is 22.4 liters only because it's at STP. So that's very similar to 66 and 99. So that would be 2/3. And then I can divide 2 by 22 and make 1 and 11. So 3 times 11 is 33 liters roughly. Now I'm going to do the same thing with my HBr. I have 324 grams of HBr. 1 mole of HBr is about 81 grams. And there's 2 moles of HBr for every 1 mole of hydrogen. And 1 mole of hydrogen is still 22.4 liters. So 80 goes into 32 4 times. So that's 1 and 4. And then 2 and 22 is 1 and 11. So 4 times 11 is around 44 liters. So our answer is the smaller of the 2, or C. Go ahead and solve this one. Restart when you're done, or if you get stuck, again, go ahead and try solving without a calculator to practice that. So they gave you 2 numbers, grams of zinc and a 0.1 molar HBr solution. They didn't tell you the volume of HBr, that's what you're trying to find. Remember that molarity is moles per liter. We don't know moles and we don't know liters, so we can't start with molarity. So that's going to be a conversion factor. We have 0.1 moles of HBr for every 1 liter. So I'm going to start with 13.1 grams of zinc. And just as before, there's 65 grams of zinc in 1 mole of zinc. I'm trying to get to HBr, so I need my mole to mole ratio. 1 mole of zinc for every 2 moles of HBr. And I could stop and then plug into my molarity equation, or I can use my conversion factor of 0.1 moles of HBr for every 1 liter. So reducing this down, 2N66 is going to be 1N33. And then 33 times 0.1 is 3.3. So 13 divided by 3.3 is around 4, because 4 times 3 is 12, but 4 times 3 is around 13. So that means my answer is D. Go ahead and pause and figure this one out. Restart when you're done. So we had lead 2 nitrate and lithium bromide. They reacted, and this is what we have left. If we notice, we don't have any bromides over here. So all the bromides must be in this solid, which means lithium bromide must be my limiting reactant, because I still have lead and I still have nitrate ions floating around. So lithium bromide, because the reaction contains no bromide. Go ahead and pause the video and figure this one out. Look at your concentrations of what's reacting and which ones are going to still be spectators at the end. So to start this one, I wrote my equation. So sodium nitrate I know is soluble, and this is going to be my solid. And then notice they're both 100 milliliters. So I'm just going to say 0.2 times 3. I have 0.6 sodium, 0.2 times 1, 0.2 phosphate, 0.2 times 1, 0.2 silver, and 0.2 times 0.1, 0.2 phosphate, or nitrate. When it reacts, I'm going to have sodium ions floating around with nitrate ions. So my sodium and nitrate are going to be the highest amounts, but notice that sodium I have more of than I have nitrate. So sodium is going to be my largest amount, and then nitrate, because both of those are going to be ions still in solution. And it wants to know the order of ions, concentration in solution. And we want it from highest to lowest. So the highest concentration should be sodium. Oh, so then D must be my answer. Next would be nitrate, because both of these are spectator ions, and the spectator ions will always be the highest in concentration, unless you have just a large amount of the excess, which in this case would be either phosphate or silver. And then of these two, I'm going to need 3 times as much silver as I do phosphate, which is why silver's not listed here, because all the silver is in the solid, kind of like what we saw a second ago with bromine. So we still have a little bit of phosphate left over, which is why it's the least concentrated, but it is still in solution. In this section, we also introduced titrations. We'll be learning more about titrations in Unit 8. But here we get a brief introduction or brief reminder about them. So I would read through this slide, making sure to pay close attention to the underlined sections. So the equivalence point is when we have equal amounts of acid and base. So moles acid equal moles base. So one equation that you can use, but only at the equivalence point, is MAVAIA equals MBVBIB. M is your molarity, V is your volume, and I is the number of hydrogen or hydroxides on the acid or base. So on A, it says that we want to know how much NaOH was delivered in the flask. So step 1 is figure out the volume of these burettes. Restart when you're done. So this is 5, this is 6. So our answer has to be 5 point something. It can't be 6 point something, because that wouldn't make any sense to have 6 point something going up to 7. But it's not going up to 7, it's going up to 5. So with your burettes, again, pay close attention to the numbers on it. It goes down. So this is 5.5, this is 5.6, this is 5.7, so 5.65 milliliters. Over on the right, we have 37.8 and it's right on that third one, so 3. But with burettes, you have to guess 1. Just like all instrumentation, it's what you can read accurately plus 1 more for sig figs. Well, I can read what I have written accurately, so I need 1 more. I'm guessing that it's right on the 0. To figure out how much the student used, I would subtract those. Make sure that you show that subtraction step, since that's the only thing that you are doing in the problem is subtracting. So you got 1 point for 31.65 milliliters. Remember, when subtracting, we want the same number of decimals, and they both had 2 decimals. So our answer to A was 31.65 milliliters. So then B says, based on that answer, determine the concentration of acid that was recorded in the student's lab report. Well, the student reached the equivalence point, and so we can use the equation MAVA IA. Our molarity of the acid is what we don't know. The volume was 25 milliliters. And it says that it's a monoprotic acid, so we know I is 1. Our base molarity they gave us. We calculated the volume of base, and there's 1 hydroxide on NaOH. So that was one way you could have done it. Or you could have said, well, let me use my molarity equation. You know the molarity of NaOH, and you know the volume of NaOH. That will give you the moles of NaOH used, which has to equal the moles of acid. So then we have our moles of acid, and we divide by our volume of acid used. Regardless, we'll get 0.139 molarity. So the last one says that the student accidentally used more NaOH. Would this error increase, decrease, or have no effect on the calculated acid concentration? When given an error analysis like this one, if you get confused and you're like, I'm not sure, you've just solved for the volume. You just solved for the concentration of the acid. We have our volume of NaOH, so if I plugged in 35 milliliters here and then resolved it, I would get a larger concentration of acid. In fact, it'd be 0.154 molarity. So you could use this formula for your explanation. Say it would increase as shown below. If I use 35 milliliters, I would have more moles of base used. Therefore, it would seem like my concentration of acid is greater. I could have also done the same thing down here by, again, just changing my volume to a bigger volume, calculating it, showing that I have a greater moles of base, so I have a greater moles of acid, which gives me a greater molarity. But besides doing math, I could have also just explained it. So increase, since it would appear more NaOH was needed to neutralize the acid, the calculated moles of base would be greater, which would lead to greater moles of acid and greater calculated molarity of the acid. And here's the answer that was on the rubric. But again, make sure that you're actually answering the question and then explaining why. There's 3 types of reactions that we're going to be talking about for the rest of this unit, which is acid-base. We're not going to talk about it as much, but acid-base reactions involve the transfer of 1 or more protons. So if it asks you to explain if it's an acid-base reaction and how do you know, you should be referring back to the protons and how are the protons transferred. Oxidation reduction reactions involve the transfer of 1 or more electrons. And then precipitation reactions involve the mixing of ions in aqueous solutions to produce an insoluble or sparingly soluble compound. And super important, all sodium, potassium, ammonium, and nitrate salts are soluble in water. Notice you don't have to have the solubility rules memorized except those four. Some people use SNAP. Sodium, nitrates, ammonium, potassium are always soluble. You will need to identify oxidation numbers. So you can read through your oxidation rules. For oxygen, oxygen's always a -2 unless it's in its elemental form, which would be O2, or a peroxide. Peroxide would be like H2O2, Na2O2. Most of the time when you see oxygen, it's going to be a -2. But a few times it comes up as a peroxide, where it looks like it should be reduced, but it's not. When an atom or ion loses electrons, it's called oxidation. So Leo, loss of electrons, oxidation. And when we gain of electrons, that's reduction. Gur, so Leo goes gur. Or you can go oil rig. Oxidation is loss, reduction is gain. So on here, go ahead and ID your oxidation numbers. Figure out who was oxidized, who was reduced, and what the oxidation numbers went to. So how we would do that is, the easiest one to start with is anytime you have an element by itself, it's always 0, like we saw as rule 1 on the previous slide. Hydrogen is a +1, oxygen a -2. -2 times 3 is -6. 1 times 1 is +1. And it said they had to add up to 0. So 1 plus something plus -6 equals 0, so that must be a +5 for nitrogen. Over here, oxygen's a -2 times 2, that's a -4. So nitrogen must be a +4 to cancel that out. Nitrate is a -1. -1 times 2 is -2. So copper is a +2. So at this point, we've seen our two things that changed. And so nitrogen gained electrons because it became less positive. So nitrogen was reduced. It went from a +5 to a +4. Which means copper was oxidized. It went from a 0 to a +2. It became more positive. So oxidation, more positive, reduction, more negative. So for this next one, we have oxygen and hydrogen. Well, hydrogen is always a +1 unless it's with a metal, and it's not with a metal. So +1 times 2 is a +2. Oxygen's a -2. -2 divided by 2 is a -1. This is when oxygen is a -1, it's a peroxide. There's not a rule about lead or sulfur, so you're going to revert back to what you know. Sulfur is going to make a -2 charge, so lead makes a +2 charge. Over here, sulfate is a -2, so lead must be a +2. Oxygen's a -2 times 4 is -8. So in this case, sulfur has to add up to 0, so this must be a +6. And then oxygen's a -2, hydrogen's a +1. So here we have sulfur changed. And we also had oxygen change. Oxygen became more negative, so it was reduced. It went from -1 to -2. And sulfur went from -2 to +6. Something has to be oxidized if something is reduced. You can't have both things, or both substances gaining electrons or both losing electrons. All right, go ahead and pause the video and do these two reactions on your own. Restart when you have your two reactions. So for the first one, you should have gotten those oxidation numbers. So sodium went from 0 to +1, so it was oxidized. Hydrogen went from a +1 to a 0, so it was reduced. For the second one, you should have gotten those oxidation numbers. So carbon went from a +2 to a +4, and iodine went from a +5 to a 0. Go ahead and pause the video and figure out which of these is not a redox reaction. Restart when you're done. The easiest way is to find zeros. The easiest way to identify a redox reaction is if there's something with a 0 oxidation number. That doesn't identify all redox reactions, but it can at least help narrow it down if you have a problem like this. For instance, in A, mercury and oxygen both have oxidation numbers of 0, but over here on the left are our reactants. They would not be zeros. It would be a -2 and +2. So A is definitely a redox reaction. Same thing B, we have 2 zeros, has to be a redox reaction. C, we also have 2 zeros, so that's redox. D doesn't have any, and then E, there's a 0, so E also can't be the correct answer. So D must be the one that is not a redox. If you had 2 that didn't have a 0, then you would need to go through and actually assign oxidation numbers to see which one didn't change. We also have acid-base reactions. And in an acid-base reaction, remember we said that protons are going to be transferred. Two definitions that you need to know is Arrhenius. Under Arrhenius, acids give off hydrogen, bases give off hydroxide. They're your most common acids and bases that we use. Acids are going to be starting with H, and they give off that H, while bases are going to end in OH. But that's a very narrow definition, so we have Bronsted-Lowry. Acids donate a proton, bases gain that proton. And with Bronsted-Lowry, we have conjugate acid and conjugate bases, which are acids and bases of the reverse reaction. So go ahead and pause the video and figure out of these two reactions, who's the acid base, conjugate acid, and conjugate base. So the first thing you need to do is find conjugates of each other. HF and F are conjugates of each other. Conjugates can only be separated by one hydrogen. Of those two, HF has more hydrogen, so it's the acid, and F has less hydrogen, so it's the base of the pair. HF loses a proton to turn into F negative. F negative will gain a proton to turn into HF. So it's an acid in the forward reaction, and it's a base in the reverse reaction. So these should technically be double-headed arrows. Then H2O and H3O are conjugates of each other. H3O has more hydrogen, so it's the conjugate acid, and H2O is the base. So H2O would gain a proton from HF, so that makes it the acid. H2O gains a proton, making it the base. In the reverse reaction, H3O transfers a proton to F, making it the acid, and F negative the base for gaining that proton. On this one, a little bit more complicated because we had conjugates. This one, a little bit more complicated because we had spectator ions still in there. But these two are related to each other, so they're conjugates. And those two are conjugates of each other. If we eliminate the spectator ion of sodium, then you can see it a little bit more clearly. So carbonic acid is going to lose a proton to OH, so it's the acid, and NaOH is the base. And then in the reverse reaction, H2O is going to lose a proton, so it's the conjugate acid, and this one's the conjugate base. Notice the two that are related to each other have to be opposites. You can tell the strength of a weak acid by its Ka value. The larger the Ka value, the stronger the acid. So go ahead and solve this one based on that statement there. So we're just looking for the strongest acid, which means the biggest Ka value. -4 is bigger than -8, -10, and -5. Since these have the same exponent, I can look at the number in front. 6.8 is bigger than 4.5, so HF is the strongest acid of these 5. Well, the strongest acid produces the weakest conjugate. So the stronger the acid is, the weaker its conjugate base will be. Based on that sentence, figure out which of these acids would have the strongest base. Well, the strongest base would be the weakest acid, and the weakest acid has the smallest Ka. Well, -5 is smaller than -4, and 1.8 is smaller than 6.3, so this one would have the strongest base. Its base would be that, since it would lose a hydrogen. Another problem that the AP test loves is given a reaction and the K, or equilibrium constant for the entire reaction, figure out which is the strongest acid or which is the strongest base. The reaction always proceeds in the direction of using the strongest acid and strongest base. Notice that this K value is above 1. So the reaction would proceed as written. If it proceeds as written, this must be my strongest acid, and this acid must be the weaker acid. The weaker the acid, the stronger the base. So my strongest acid in this reaction is HNO2. That is not a strong acid, but it's the strongest acid of this reaction. So my strongest base will be acetate ion. Again, not a strong base, but it's the strongest base of this reaction, because the reaction always proceeds to use up the strongest acid and the strongest base. And since our K is above 1, we know that the reaction is proceeding as written. So go ahead and pause the video and try this one on your own. Restart when you're done. Since the K is less than 1, that means that my stronger acid and base must be on the product side, because the reverse reaction is favored. So HF, this one must be my stronger acid, and HS must be my stronger base. So F negative is a stronger base. Nope. HF is a stronger acid. Yes. The conjugate, these are not separated by just a hydrogen. And remember that these are not conjugates of each other. Those are conjugates of each other. And these are conjugates of each other. So our answer is B. You may also have to balance redox reactions. We'll be talking more about redox and redox reactions in Unit 9. But remember that your electrons have to cancel. So make sure that you multiply your reactions to make sure the electrons cancel out. Go ahead and pause the video and try this one on your own. Restart when you're done. So you should have multiplied that top reaction by 2. And so the coefficient in front of Fe plus 2 would just be a 2. Same thing, go ahead and pause and write the balanced net ionic equation for this reaction that would take place. For this one, we needed to multiply our bottom reaction by 2. Our electrons are already on opposite sides, so we don't have to worry about which one we would flip. Make sure that you have a 2 in front of potassium metal and potassium ion and bromine ion. And make sure that you have charges on potassium ion and bromine ion. Notice that we don't have the electrons in there because they would have canceled out. And finally, go ahead and identify each of the reactions as either acid-base, precipitation, or redox, and then justify your answer. Restart when you're done. So the first reaction you should have said was precipitation, because we had two aqueous solutions producing a solid. That solid was silver chloride, which is the precipitate. And then for the second reaction, had you gone through and looked at your oxidation numbers, anytime we have a 0, it's most likely redox, and it was. So redox electrons are transferred in the reaction, which is shown in the change in oxidation numbers. Sodium went from a 0 to a +1, and calcium went from a +2 to a 0. So you couldn't have just stated that. You needed some evidence. Our evidence is the change in oxidation numbers and actually stating what those oxidation numbers were.